Good morning, students. We have been discussing so far on time-dependent perturbation theory. The main application for time-dependent perturbation theory is to study the induced absorption, stimulated emission, and spontaneous emission that we know already. And of course, we have been studying in terms of classical treatment. So, semi-classical treatment. We have taken the results of classical statistics, especially Maxwell-Boltzmann statistics, and we have taken those results and compared with the quantum results, and we have obtained the results. And the main concept will be on light interacts with the matter. So when light interacts with an atom, so we have the transition will take place. So when light interacts with an atom, the electron will be excited to the excited states and will go to the excited states many levels and it will come back. When it comes back, it cannot go into specific level. It can go into many levels. I repeat, so when the excited electrons, they will go into many excited levels. Okay, when they come back, they cannot come into the one particular level. It can go into many levels. This has to oblige certain rules, what we call this as selection rules. So very, very important one. So we are going to discuss the selection rules today. So it has to obey certain rules, what we call as selection rules. These selection rules, they depend on orbital quantum number and magnetic quantum number, which we will see now. And these transitions, and they will oblige on dipole approximation, especially electric dipole approximation. And of course, as I said, when light interacts with the matter, the electrons, all the electrons or many electrons will go to the excited state depending on the energy they gained from the external perturbation. So now charged particles are separated. So there exists dipole transition, dipole approximation. So what we call this as electric dipole approximation. And of course, we know that the magnetic field of light, electromagnetic wave, they will also interact with the magnetic moment of the atom. That's called magnetic dipole approximation, which we are not going to discuss. So there are two transitions, two approximations. One is electric dipole approximation, another one is magnetic dipole approximation. And magnetic dipole we are not going to discuss. So we are going to discuss only electric dipole approximation. The very important thing is there must be certain values of electric dipole approximation. Electric dipole approximation will have finite values. Only then the transitions will occur. Suppose if it is equal to 0, so there will be no transition. Those transitions are called forbidden transitions. I repeat, there exist certain values of electric dipole approximation, only then the transitions will occur. Okay, those transitions are called allowed transitions. If the value is 0, if the value of electric dipole approximation is 0, there will be no transitions. Those transitions are called forbidden transitions. So which we are going to see elaborately today, and the title is Semi-Classical Treatment of an Atom with Electromagnetic Radiation, and thereby we are going to discuss in detail about the selection rules. The quantization of electromagnetic radiation field is used to treat the absorption and emission of electromagnetic radiation by atoms and molecules. This is called quantum field theory. But here we are going to discuss a semi-classical treatment. As I just now I said that we are going to take the results of classical statistics and we are going to apply into quantum mechanics. So a semi-classical treatment which probes considerable effect of absorption and emission to study the induced absorption and stimulated emission and spontaneous emission. Generally, the wavelength of radiation in the visible region to radio frequency region of electromagnetic spectrum is very large. Suppose the wavelength of EM, electromagnetic wave, is very large, larger than the size of the atom or ions or molecules, only then the electric dipole transition will occur. Suppose if it is very, very small, the wavelength of radiation is small, then we are going to consider the atom itself as a charge. Okay, if it is larger, we are going to use dipole approximation. So hence when the light interacts with the atom, we are going to have an approximation of replacing the atom by an electric dipole, because the charges will be separated. This approximation is called a dipole approximation. As I said earlier, the study of absorption and emission will lead into dipole moment. Okay, dipole moment. Dipole moment is given by the separation of charges multiplied by the distance. So mu ml is equal to minus er. Okay, so this is what we have already studied. Mu ml equals minus er. Okay, so now this is the expectation value, matrix element. Okay, ERA, and RA is the component. RA is the component of R in the polarization direction. So this is nothing but Z. Z equal to R cos theta, which is equal to RA. Okay, component of R. So when the wavelength is larger compared to the dimension of the atom, then the radiation will see as dipoles. Suppose if it is smaller, then we can probe this as individual charges, not the dipole as a whole. Okay, so these two conditions. When a charged particle interacts with the electromagnetic field, the transition takes place from initial state to the final state. We know already. Okay, and one can determine the probability of transition rate. So this is what we have been doing in time dependent perturbation theory. So we have obtained the transition amplitude. Can you remember? So this is what we know already. One can determine the probability of transition rate from initial state to final state. One of the most important applications of time dependent perturbation theory is to study the interaction of atoms with electromagnetic field. Such an application reveals a great deal about the structure of the atoms and molecules. For simplicity, we assume that only one atomic electron is involved in the interaction, and we have neglected the spin for the simplicity. Okay, electron spin we are not going to take into account for the calculation. Then another main idea is we are going to introduce two factors in the Hamiltonian. So in the Hamiltonian we are going to introduce two factors. One is the vector potential, another one is scalar potential, which they involve in electromagnetic radiation. So we have electromagnetic waves in which we have electric field and magnetic field. Okay, we know already. So electric field and magnetic field. So electric field of course depends on this factor, okay, phi of r, and magnetic field depends on this factor, vector potential. This is where scalar potential and this is where vector potential. This is related with the magnetic field, this is related with electric field. So we are going to introduce these two through the Hamiltonian, through the momentum. So we will see now. So in the absence of external perturbation, the Hamiltonian of the atomic electron is given by kinetic energy plus potential energy equal to total Hamiltonian. This is for the unperturbed Hamiltonian. So we know already this, where m is the mass of the electron and V naught of r is a static potential due to the interaction of the electron, which screens the other electrons as well the nucleus. Okay. So now if the electromagnetic radiation of vector potential A of r comma t and the scalar potential phi of r comma t is applied on the atom, then the Hamiltonian due to the interaction of the electron with the radiation is given by this equation. So your P is replaced with P plus E by C vector potential. Okay, this also we have seen earlier in quantum mechanics 1. So P is replaced with this factor, and this factor belongs to magnetic field, and we have introduced electric field, this term. So this is electric potential, this is your vector potential due to magnetic field. Okay, electric and magnetic field, what we call this is electromagnetic spectrum. So your H equals your total kinetic energy, your potential energy, and this must be your scalar potential. Now this is squared, so we can multiply these two like this. Okay, so now this is a vector quantity and also operators, so we'll have to be more careful with the operation. So P multiplied by P, first we are going to carry it out, then after that P multiplied by this factor, A multiplied by P, then A multiplied by A. So there will be 4 factors. P multiplied by P will give you P square. Okay, then P multiplied by this factor will give you E by C P dot A. Then this multiplied by this will give you A dot P. This multiplied by this will give you E squared A squared by C squared. Is it okay? Simple one. Other terms are let it be like this. Now P dot A operates on psi. So everything operates on psi. H psi equal to E psi, eigenvalue equation. Now you consider this one, this part alone, second part alone. P dot A operates on psi. You will have to keep this as constant, you will have to differentiate. You will have to differentiate this, you will have to keep this as constant, as usual. So in that case, this will be written as AP psi plus PA psi. So this will be replaced by this one. A dot P plus B dot P. Okay. Now already one A dot P is there. So put together that will give you 2 A dot P. So this will be as it is, where P is replaced with minus IH cross del. So you have minus IH cross del dot T. And this is your E squared A squared by C squared. Other terms are not like this. Is it okay? Any doubt? Okay. P dot A is replaced with 2 factors. You are going to replace this one. You have 2 things, and this is added with this, you will have this term. And we know that the perturbed Hamiltonian itself will be very, very small. We know already. Small perturbation only can be applied. Okay, this is also a perturbation. Everything is a perturbation here except this term. This is unperturbed. We know already. P square by. Other things are all perturbed due to the external magnetic field and electric field. This is also perturbation. Okay, if perturbation is very small and A square will be very, very small. Okay, this is very, pretty small, and A square will be again very, very small. So we can neglect the last term. Okay, so now total Hamiltonian, I have written the same equation. Okay, I have written the same equation, and I am going to assume that phi of r comma t equal to 0, for which the radiation with no static electrostatic source, since del dot A equal to 0 for a Coulomb gauge, and neglecting the term related to A square, as I said the argument. So you will have del dot A this equal to 0, you will have this term P square, and this term will be there, this term will be 0, this term also neglected, and you have 2 A dot P alone. Del dot A equal to 0, this term is so small we can neglect, and this term we are going to consider no electrostatic source, and we can have the equation exactly 7.131. Okay, so this is your unperturbed Hamiltonian, this is your perturbed Hamiltonian. Okay, perturbed system. So this can be replaced with your H naught, the remaining term let it be like this, and 2 gets cancelled. So you have H equals H naught plus E by M naught C A dot P, and this term can be written as V of T, where V of T equals this term, which is the interaction between the electron and the radiation, electromagnetic radiation, and it is very small compared to H naught. So that's a condition for any perturbation theory. So perturbed Hamiltonian or system should be very, very small. Okay, is it okay? Thus the classical treatment is valid. So we have taken only from the classical treatment is valid when a large number of photons contribute to the radiation. When the intensity of the radiation is too high, we are going to have only wave nature. If it is low intensity, we are going to have particle nature. So dual characters. Okay, dual character of your matter waves as well light waves, so that the quantum mechanical treatment of the electromagnetic radiation will be considered. Hence, we would necessarily replace the various fields E of r comma t, your magnetic field and your vector potential with the corresponding operators. Now we will go for the second type. As I said that the levels, all the excited levels, when they come down, they allow to oblige certain transitions. Those transitions, if dipole transition has some values, then what we call this is allowed transitions. Okay, it all depends on the value of the dipole moment. If there is no dipole moment, there will be no transition, forbidden transition, and it has to apply certain rules. What we call this as selection rules. Selection rules for dipole transition, and we are going to discuss only the electric dipole transition, not magnetic dipole transition. So electric dipole transition only we are going to discuss. So we know that the transition probabilities for induced absorption, stimulated emission and spontaneous emission are done to evaluate the electric transition dipole moment. Okay, we are going to evaluate the transition dipole moment. The expression of the transition dipole moment between two states is given by this equation. So we know already this. Correct? Your dipole moment is given by minus ERA, where RA is a component of R in the polarization direction. So here the transition among all states are not allowed. Transitions from all states are not allowed. Okay. The selection rules specify the transitions that may occur on the basis of dipole approximation. Okay, on the values of dipole approximation, which we are going to see now. The transitions for which the transition dipole moment is non-zero are allowed transitions. Okay, or non-zero. If values exist, that's called allowed transitions. If values are zero, forbidden transition. And those for which it is zero are forbidden transitions. The transition dipole moment can be considered as a measure of imbalance created in the electromagnetic field when the electron makes a transition between two states. Now it's very important how we are going to calculate in terms of symmetry operation, which we learned in quantum mechanics 1 under parity. So this is about parity operation. We are going to discuss whether there exists the values of dipole moment exists or not. So we are going to discuss. So this is the expression for your dipole moment. Okay, this is the expression for dipole moment, which you have seen already. Okay, if there is a value, this is called allowed transition. If there is no value, it is equal to 0, this is called forbidden transition. Okay, we are going to check whether there is a value with the help of symmetry operation under parity. Parity means just mirror reflection. If x is there, minus x, y minus y, z minus z. Okay, when you go for spherical polar coordinates, this will be r equals r, and your theta will become pi minus theta, and your phi will be pi plus phi. So this is the condition is. Now in order to occurrence of the transition, the dipole matrix element must be finite. If there is a transition, the dipole moment value should exist. It must be finite. It should not be equal to 0. Okay, now we will go for this. And as I said, RA, I have pulled minus E out. Okay, RA sandwiched between your ket vector and bra vectors. Okay, this is what. Now this is your initial vector, and this will be your final vector. If initial vector is odd, final vector must be even. If initial vector is even, final vector must be odd. You remember this. Initial vector is a normal vector, and final vector will be always a complex vector, excited state. The wave function will be always in a complex mode. Okay, so as I said, if it is even, this must be odd. If it is odd, this must be even. Now we will go for this center one. What is RA? RA is nothing but the component of R, as I said, which is nothing but Z equal to R cos theta. The component of R. Z equals R cos theta. So R cos theta. As I said, for any parity, theta becomes pi minus theta. You substitute in that equation. So R cos pi minus theta, which is nothing but minus R cos theta. Cos pi minus theta is minus cos theta. So you will get minus R cos theta. So this under parity, this will be odd number. So is it clear? This will be your odd number. Z equals R cos theta. You substitute for theta pi minus theta. Cos pi minus theta is minus cos theta. So this will become minus R cos theta. So minus Z, which is nothing but your minus R. So this will be your odd number under parity. Now you are going to multiply all the things. Now, if it is, as I said, if it is even, this must be odd. So even multiplied by R or odd multiplied by even will give you always odd number. Odd multiplied by even or even multiplied by odd will give you odd number. Odd multiplied by odd will give you even number. The result of these things will be odd. Odd multiplied by odd will give you even number. If it is even number, value exists. If it is odd, there will be no value. Is it okay? If final answer is odd number, there will be no values. It will be equal to 0. This is very easier one. Okay. If final one is even number, then there exists values. So it will be finite. Okay, so here the value is finite because ultimately we are able to get only even number, even parity. Even parity. So even parity means there exists a value, so which is called finite. So transition will occur according to the values of dipole transitions. Is it okay? So for non-zero transitions, the initial and the final state should have always different parity. So different parity. If it is odd, it must be even. If it is even, this must be odd. So different parity. So for hydrogenic atoms, the systems are specified by the usual quantum numbers. We know that principal quantum number, orbital quantum number, and magnetic quantum number we know already. So we can write this as R sandwiched between LMM. So your ket vector and bra vector. We can write this as in terms of xi plus yj plus zk. So this can be written as exactly like this. Okay, very simple one. Now we are going to separate. First we will go with if the radiation is a plane polarized and the electric field is in the z direction. We are going to consider that electric field is in the z direction. And we are going to take only one component, which is nothing but your z direction, which is nothing but your r cos theta. Simple one. Okay, when you are going to take r cos theta like this, you are going to take the phi part, which is nothing but e power I m phi. We have written for phi part it will be e power I m phi, but here n dash l dash m dash is given. So m minus m phi d phi. So this must be finite value. If it is a finite value, then this value should be m dash minus m, which must be equal to 0. So this is one condition. M dash minus m is nothing but your del m. So this is one selection rule. Del m should be equal to 0. First one selection rule. Del m. Your m dash minus m should be equal to 0. Only then there will be a value. It must be finite. If it is finite, the dipole approximation will be finite. If dipole approximation is finite, only then transition will be allowed transition. We allow only transition, emission transition. Is it okay? So everything depends on this. Now we will go for xy. So earlier we said about z direction. Now we will go for xy plane. So if the radiation is polarized in the xy plane, then we have to calculate the matrix elements of x and y. So we can evaluate the matrix element of x plus or minus iy. So x is given by this equation and y is given by this equation. In terms of polar coordinates, we can write x plus iy. X plus iy can be written as like this. You pull r sin theta out. So that will give you cos phi plus or minus I sin phi. So this can be written as e power plus or minus I phi. Okay. So we can write this as exactly in the expectation value in terms of expectation value like this r sin theta e power plus or minus I phi. And I can turn this r sin theta as f r comma theta out. The remaining term I can write as I have written exactly like this. See, I have written it. Only thing is m minus m dash plus or minus 1 because here it is plus or minus I phi. Now again this must be a finite value as we discussed. This must be a finite value. This must be a finite value. The condition goes with m dash minus m, which will be plus or minus 1. Only then this condition will be satisfied. If del m equals plus or minus 1, only then this value will be finite. Okay. Earlier case, if del m equal to 0, only then this value will be finite. So similarly, if this must be finite, this condition should be satisfied. M dash minus m, which is equal to del m plus or minus 1. So second selection rule. Combining these two will give you the total selection rule for magnetic quantum number del m. Okay, change in magnetic quantum number will be 0 and plus or minus 1. Is it okay? Similarly, one can obtain the selection rule for orbital quantum number, which is nothing but del L equals plus or minus 1. So we have third selection rule. The first selection will be del M equal to 0. The second one will be del M equals plus or minus 1. And third one will be del L plus or minus 1. So three selection rules that we have obtained so far. And it may be linked to the spin angular momentum of the photon, which is equal to 1, because it's general one. When the photon is emitted or absorbed to conserve the total angular momentum, the orbital angular momentum of the electron in the atom changes by plus or minus 1. Okay, it changes by plus or minus 1. So as I said, the total selection rule is exactly like this. Del L plus or minus 1 and del M equals 0 plus or minus 1. An absorption or emission of a photon may increase the orbital angular momentum of the electron depending on the orientation of the electron's angular momentum of the photon. Okay, there are the interaction between photon and atom, interaction between light with matter. So photon and atom. So we'll have to go only with the angular momentum of both. Okay, hence the total selection rules are given by this. Okay, as we discussed already, in the case of electric dipole transitions, we discussed the initial and the final states will have different parities. If it is odd, it must be even. If it is even, it must be odd. Now, very important one. Okay, how the transition occurs. Okay, this is now just to consider this figure. This is L equal to 0. Okay, this is for 1s state. This is for 2s state. Here also L equal to 0. Okay, 2s state. L equal to 0. This is 1s, this is 2s. The transition will never occur between these two states, forbidden state. Because L equals plus or minus 1, correct? Del L equals plus or minus 1. Here it is 0, L equal to 0. Here also it is L equal to 0. Doesn't satisfy this condition which it satisfies. Del L equals plus or minus 1. You consider this one, L equal to 0, 1 state. 1p state is L equal to 1. That will give you del L equals plus 1. See, it satisfies that condition. So here transition is allowed transition, and this must be forbidden transition. That's all. So as a result, the electric dipole transitions like 1s 2s, 2p 3p are not allowed. They are forbidden. While transitions like 1s 2p, see, 1s 1p, 1s 2p, 2p 3s are allowed. So forbidden transitions and allowed transitions depending on the selection rules. Del L equals plus or minus 1 and del M equals 0 and plus or minus 1. Is it okay? Now generally we can look into the picture. This is very important one. It's easier also. So you have orbital quantum number here. We have principal quantum number here. Okay, so you have various states, 1s, 2s, 3s, 4s, and you have 2p, 3p, 4p, 3d, 4d, and 4f. Okay, here the transition allowed or not? Just tell me whether transition is not allowed. It's forbidden, no transition. Okay, forbidden because L equals 0. Okay, so selection rule doesn't go with. So here it is not allowed. What are this into this? Here it is 1 and 0, your L. So allowed transition. So 2p to 1s, it's allowed. We'll go for 3p now. Again it is 1, 1, 0, 0 and 1. So 3p to 1s is allowed. Similarly 3p to 2s also is allowed. What about 4p? 4p, 3s is allowed, 2s is allowed, 4p to 1s is allowed. So allowed transition. Whereas 4p to 3p not allowed, forbidden. 3p to 2p is not allowed, forbidden. What is 4s to 3p? Yeah, it is allowed, 0 and 1. Minus 1 and plus 1. Del L plus or minus 1, 0 and 1. So 4s to 3p allowed. Similarly 4s to 2p also allowed. Allowed transition. We can go with again 2 and 1. Plus or minus 1. Plus or minus 1. 4p to 3d minus 1, 4d to 3p plus 1. So again 4d to 2p is allowed. Is it okay? Very simple one. Similarly you can go for this one, 4f to 3d it's allowed. Similarly 3d to 2p it's allowed. 4f to 2p not allowed. It comes on plus or minus 2, so which is not allowed. Is it okay? So selection rules are very simple one. According to the selection rules only we are going to get the transition, and then depending on the dipole transition value occurs. Okay, the conclusion. When a photon is emitted or absorbed, to conserve the total angular momentum, the orbital angular momentum of the electron in the state changes by plus or minus 1. So orbital quantum number plus or minus 1. An absorption or emission of a photon may increase the orbital angular momentum of the electron depending on the orientation of the electron's angular momentum with the angular momentum of the photon. So as I said, so there will be interaction between the angular momentum of the photon which is coming inside and the angular momentum of the atom. So there will be interaction. The selection rules which we have discussed are valid only for the dipole transitions which exist, which has a finite value. If it is 0, there will be no transition. If it exists, there will be a transition, allowed transitions. So the magnetic component of electromagnetic waves can interact with the magnetic moment of the electron in the atom. What we call this as magnetic dipole moment, as I described earlier, but they are very weak. Very weak in the sense it will be 10 power minus 5 times less. Okay, compared to that of electric dipole transition. That's why we neglect. Otherwise, we can add. So you can add with electric dipole transition with magnetic dipole transition, but you can't add because this is 10 power minus 5 times lesser. So you can't add. It will be 0.0001. So 10 by 5 times lesser. So which is not possible. So that's why they have neglected magnetic dipole transition. Only electric dipole transition alone occurs, and depending on the selection rules. Okay, so that is the end of this whole unit. So the whole unit we discussed so far about time dependent perturbation theory. Okay, so thank you students. We'll see you in the next class. Bye students.